Hello everyone, welcome to the 25th episode of this series. In this video, we'll talk about linear independence. So last time, we learned about spans and spanning sets and a lot of different ways to describe the same thing. So spanning sets are good because we can write subspace in terms of a few potentially finite number of vectors, and we can use those finite vectors to recreate every possible vector in the subspace. But sometimes we might have more elements in our spanning set than we need, and when that happens, this construction is not really an efficient construction. So let's look at an example. So let W be the subspace consisting of vectors in R3 whose entries are the same. So W contains all possible vectors which have all the same entries in the three coordinates. So one can check that uh, the set containing the vectors 3, 3, 3, 7, 7, 7, and -5, -5, -5, and the set containing the vector 1, 1, 1 are both spanning sets for W, but the first one is obviously less efficient because we are using three vectors to describe this set when we can just use one. So what happens is that we can write the zero vector using two different linear combinations of the vectors in the first set. So we can write 1 times 3, 3, 3 plus 1 times 7, 7, 7 plus 2 times -5, -5, -5, and that gives us the zero vector. And we can also write 0 times 3, 3, 3 plus 0 times 7, 7, 7 plus 0 times -5, -5, -5, and that also, of course, gives us the zero vector. So how do we measure how efficient a spanning set is? So one way to do it is by checking how many ways the zero vector can be written as a linear combination. So to unravel this more, let's first look at a definition. So the trivial linear combination of a set of vectors v1 through vn is just the linear combination where all the coefficients are zero. So 0 times v1 plus 0 times v2 dot 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 plus 0 times vn. So this linear combination is called the trivial linear combination. And set of vectors is linearly independent if the only linear combination which is equal to the zero vector is the trivial linear combination, which means the only time a linear combination of a set of vectors is going to give us the zero vector if all the coefficients were zero themselves. And of course, a set of vectors is called linearly dependent if it's not linearly independent. And note that this definition makes sense for any set of vectors in the space Rn. Let's look at an exercise. So we want to show that the set given by just the vector 1, 1, 1 is linearly independent, while the set given by the vectors 3, 3, 3, 7, 7, 7, and -5, -5, -5 is linearly dependent. So first, we'll work with S2. So from the previous example, we already know that there are two different ways of writing the zero vector as a linear combination of 3, 3, 3, 7, 7, 7, and -5, -5, -5. Note that the linear combination on the right is the trivial linear combination. Now, because there are two different ways of writing the zero vector as a linear combination, we conclude that S or S2 cannot be linearly dependent. On the other hand, if we set the linear combination of the vector 1, 1, 1 equal to 0, we just obtain that C is equal to 0. Because there's only one vector, we just multiply it with a constant and then we solve for all values of C that make this 0 and realize that there's only one possible value that is C equal to 0. So that gives us that there's only one way to write the zero vector, the linear combination of vectors in S1. Therefore, S1 is linearly independent. So this begs the question, how do we check if a set of vectors is linearly independent? So I want to define the concatenation of these vectors. So given a set of vectors, of the same height in some particular order, the concatenation is just the matrix with these vectors as column vectors. For example, if I have these three vectors, 1, 4, 7, 2, 5, 8, 3, 6, 9 in this particular order, its concatenation is just going to be the matrix where each column vector is one of these vectors. Now, here's an important result. A set of m vectors in Rn is called linearly independent if the rank of their concatenation matrix is m. And if this rank is less than m, then the set has to be linearly dependent. So let's look at another exercise. Here we're given, a set of three vectors, and we have to determine whether this is linearly independent or not. So we saw that the concatenation of these vectors is this matrix, and to determine whether this is a linearly independent set of vectors, we have to find out what the rank of this matrix is. So we can put this into a row echelon form and count the number of leading ones. So one matrix in row echelon form equivalent to this matrix is given by 1, 2, 3, 0, 1, 2, 0, 0, 0. And that just tells us that the rank of this concatenation matrix is 2 because there are only two leading ones. And because this 2 is less than 3, which was the number of vectors, we get that S is not linearly independent. Now here's a little fact. If V1 through V1 is a linearly independent set of vectors, then any vector can be written as a linear combination of V1 through Vn in at most one way. So you can either write any given vector as a linear combination of V1 through Vn in exactly one way, or you cannot write it as a linear combination of these vectors. So to efficiently construct vectors in a subspace, we need a spanning set, which also happens to be linearly independent, and such a set of vectors is called a basis for a given subspace V. And this is going to be one of the most important definitions in this class. For example, the set with just one vector 1, 1, 1 that we saw a few moments ago is a basis for the subspace W of all vectors of height 3 whose entries are all the same. Why? Because you can just multiply this vector 1, 1, 1 by a constant c to get any other vector whose all entries are the same. And we also saw a few moments ago that this set is linearly independent. Okay, now we can restate all these definitions that we've seen recently more explicitly. So a set of vectors V1 through Vn in a subspace V is called a spanning set for V if every element of V can be written as a linear combination of these vectors in at least one way. We call it a linearly independent set if every element of V can be written as a linear combination in at most one way. And we call it a basis for V if every element of V can be written as a linear combination in exactly one way. So let's end this episode with a little exercise. So I'm given a set of three vectors of height 3, and all I want to do is just have a strategy to show that this is a basis for R3. We're not actually going to solve this in this episode. So to show that B is a basis for R3, all we need to do is show that every element of V can be written as a linear combination of vectors in B in exactly one way. So in other words, the linear system given by this matrix equation 1, 2, 3, 0, 1, 2, 1, 0, 1 times xyz equal to b1, b2, b3 for every possible choice of b1, b2, b3 has a unique solution. So if you're wondering where this equation comes from, note that this is the same as writing x times the first vector plus y times the second vector plus z times the third vector equal to b1, b2, b3. In other words, the linear combination of these three vectors being equal to an arbitrary vector in R3. And with this, I would like to end this episode. Hopefully, things made sense. I will see you guys soon. Up until then, happy learning.